So back to our example from before, and let's talk about something we haven't talked about yet, and that is thickness. Now, you can't really see it here, and this is without a weld. So let's cut actually through this simulation to see what's actually going on. And you can actually use the clip node for that. It's a very handy tool. What that gives you is a plane that it cuts through no matter what. It doesn't give you an edge or anything. It just really cuts through and shows you the inside. But you can use that to cut through this plane, and then you can see better what's actually going on here. And what you can see is there's a pretty big gap between our sphere and our cloth plane here. And this comes from the fact that there's actually an internal thickness that we haven't talked about yet. So before we move on, let me show you that under Visualize, you can actually turn this on, and then you can see what the collision is based on, and you can see it's actually set to every point, which makes sense because Vellum is a point-based system, right? XPBD. The interesting thing is you can set this in the Vellum constraint nodes, and just where you set mass, you can also set thickness. By default, it's unchanged. In other words, it means it isn't. If you don't set it anywhere else, it will not be there. And let's actually set it to something. Set it to uniform to 001, and let's look for an attribute that was created. I cannot really tell you, even though you would by instinct think maybe that it's an attribute that is set on the constraint geometry, but it isn't. It's actually set on the geometry itself. And if we look for this number 001, we can find that there is actually only one attribute that has that, and there is no thickness attribute or anything. It's actually p-scale, interesting enough. So p-scale is actually the attribute that is set to thickness, and thickness is p-scale, which means, of course, we can set it ourselves. Let's actually quickly try that with a point wrangle, and we set it to 0.1. And you have to rewind, and there you go, it has changed. So let's change it back to something super small. And there you go, it actually has changed again. So actually it is p-scale, which is cool because you can change it yourself if you want. We will not do this, but it's good to know. So in the Vellum cloth, you can actually set it to uniform, which is just sets the p-scale. You can just leave it unchanged, and then it's 0. And interesting enough, the p-scale is still there, set to 0, and you will get, on the first frame you will see that, you will actually get a thickness that is higher than 0. And we will talk about why that is. You would think that setting the thickness to 0 makes a lot of sense, but then you will actually run into collision problems. But before we look at this, let's quickly talk about what you can set the thickness to in the Vellum constraint. You can set it to unchanged, does nothing. Then set to uniform is just a global setting. And then you can calculate uniform and calculate varying. And the logic behind this is that you get a better result in your collisions if you have different topologies on your cloth. So let's say you have a really fine resolution on one part of your cloth and a relatively coarse resolution on another part, then the calculate varying will calculate the p-scale based on the edge length. In our case, that will not give us any kind of interesting result because, as you know, our geometry that we're using here is almost exclusively made of equally sized edges. So this is more interesting for more complex cloth simulations, but just for you to understand. And calculate uniform in turn means when you have multiple objects. A good example here actually would be if we had still an edge fractured version of our piece of cloth here. So if you simulate the same cloth object that is made of multiple elements, then the calculate uniform will calculate an average p-scale for every piece that you give it. So not for the whole thing, but at least for every piece. Whereas again, the calculate varying will actually calculate it for every edge. So most of the time, for simple stuff that we're looking at, this is not important. We will almost always set it to uniform, because we're not interested in any kind of variation based on, topology or piece elements. We just need a general thickness, and we're good with that. Now let's come back to the question of why are we not just setting the thickness to 0? And for this, let's jump to another example. So let's take this example, for example, which is just a piece of cloth that falls over a bunch of wood, because why not? So as you can see at the first glance from far away, it looks pretty okay. But if we change the camera angle to shift 4, it is actually, you can see there's a gap. Now, it depends, of course, on your camera angle when you will see that. So if you have a camera angle like here, this becomes actually a problem. And also where you will see that, and this is quite important, is at render time. Very often contact problems are visible in the shadows. And this is one more reason why you should never trust the viewport, but always do a test render, because the shadows will actually kind of show what's going on, and you will see a lot of problems only when you render with proper light. Now, how do we solve this problem? Well, of course, we use the Vellum cloth for that, and by default, it's set to calculate uniform, so it comes out with some calculation based on the edge length, and the result is 00316 in the p-scale, and we could just overwrite that, so let's say set uniform. Now, why don't we just put that to 0? As we've seen before, actually, when it is 0, then the Vellum solver will automatically, and let's make sure our visualization is on, will automatically create a default p-scale, which is probably much bigger than we want. So 0 technically doesn't work, but also from the logic it doesn't work, because if the collision is based on the points and you don't have any volume around them, there will never be a collision, and this is actually not what you want. And we can show this problem by just putting a very small number in. So let's rewind so that we actually see the result, and you can see those little dots there. Those are actually now the thickness visualizers. So we have a very, very small thickness now. Let's see what happens when we do this. So massive problems in the collisions. Why is that? Well, if you think about how collisions work in any 3D program really, and this goes back to the SDF video actually, then the collision can only happen when a point is considered kind of close enough to its collision object. And when you make the points really, really small, then basically while the simulation is running, there will never be a moment where the collision is actually happening because the point is so tiny. We could actually come up with a solution for that, and that is just having more time samples. And this is actually something that works. So maybe I shouldn't go too small for this to work, but something like this should be fine. Yep, it's still there. And let's now try in this Vellum solver to change the substeps. Let's say to something like, I don't know, 7. Of course, what will happen is it will be slower, but let's see what it does with our simulation and our collision. And there you have it. The collision is actually now working. And with some exceptions here, but actually more sub-steps would actually solve even that. But you can definitely see the result is much better. And if we go back to shift 4, you can see here quite clearly that the distance is also much smaller. Of course, it's always a matter of finding the sweet spot. What you can do is you could increase the geometry subdivisions, but that's also something you try to avoid usually, especially if you already have a simulation that you like. So what I usually do is I try to find the sweet spot where I don't need too many sub-steps, but still have a good enough result, of course. But knowing that you can use both and you're not tied to only one will always give you some kind of solution. And this is really all you need to remember. You can change the thickness, but sometimes when you make it too small, you need also to increase the sub-steps. Okay, so this is about thickness and how to deal with collision problems. I hope this was helpful. See you in a later video. Cheers.